Welcome to The Explainer. Today we're diving into something that's happening right under our feet, but that we almost never think about, the surprisingly complex world of water loss in our cities. It's a hidden story of physics, engineering, and the massive, invisible network that keeps our taps flowing.
So, let's just start with what seems like a simple question. You might think the goal is zero leaks, right? No lost water. But when you have thousands of miles of pressurized pipes, it's actually impossible. The real question isn't about getting to zero, it's about figuring out what's an acceptable, unavoidable amount of loss.
To even begin to answer that, we have to get our terms straight. We're not talking about accounting mistakes or water theft here. What we're focused on is what experts call real losses. That's the actual physical escape of clean, treated water from the pipes before it ever gets to you.
Okay, so if every city has these real losses, how do we know who's doing a good job and who's not? It's not as simple as just measuring a percentage. To do it right, you have to start by setting a very specific, tailor-made benchmark for each and every city.
Right, let's get into it. Engineers calculate this thing called the unavoidable annual real losses, or UARL for short. Now, this isn't a wild guess, it's a precise calculation. It looks at the total length of a city's pipes, the thousands or millions of connections to every home and business, and the average pressure in the system. All of that data gives you the absolute rock-bottom amount of water that network has to lose, even if it's managed perfectly.
The best way to think about it, it's like par on a golf course. Simple as that. You're never going to get a score of zero, right? But par, that's the target. That's the benchmark for excellence. The URL is the par score for a city's water pipes.
And once you have that par score, grading the network's real-world performance is surprisingly straightforward. Use what's called the Infrastructure Leakage Index, or ILI. It's just a simple but really powerful ratio. You take the city's actual current water loss and divide it by that unavoidable minimum, the URL.
And here's the key takeaway. A score of 1.0, that's a perfect score, an A+. It means the city is hitting its par exactly. But if a city has a score of 2.0, that means it's losing twice as much water as it should be. And if it's up at 8.0, you've got a serious problem. This lets us compare, say, Tokyo and a small town on a totally even playing field.
This table really shows how those scores get turned into a game plan. If a utility scores in that top A1 category, trying to find and fix those last few leaks might actually cost more than the water is worth. But if they're down in category D, well, they know it's time to stop patching and start planning for some major pipe replacement. So we know how to grade a network's performance. But to actually fix the problem, we have to get way deeper and understand the physics of the leak itself. And this, believe me, is where things get really fascinating, because our whole idea of what a leak is probably wrong. For decades, the standard assumption was that a leak is just a simple, fixed-size hole in a pipe. Makes sense, right? But the reality, especially with the kinds of pipes we use today, is so much more dynamic. The leak is a shapeshifter.
This incredible insight led to a new model called FAVAD. That's short for Fixed and Variable Area Discharge. The idea is brilliant. Every leak is actually made of two parts. You've got the initial fixed hole, sure, but you also have a variable part that literally stretches and grows as the water pressure goes up.
Okay, think about those old, super rigid pipes made of steel or cast iron. A leak in one of those behaves pretty much like you'd expect. Engineers use a leakage exponent to measure this, and for these pipes, it's about 0.5. More pressure means more water loss, but it's a predictable, stable relationship.
But get this, with modern flexible pipes like PVC, everything changes. As the pressure rises, the plastic around a crack actually stretches, physically making the hole bigger. For these, the leakage exponent can jump to over 1.5. That means a small bump in pressure can cause a huge, out-of-control surge in water loss. So what's going on here? Well, it's all down to the material. Steel and iron pipes just don't have much give, but plastics like PVC are elastic. So when you increase the pressure, it's not just pushing more water through the hole, it's actively prying that crack open wider, especially if it's a long crack running down the length of the pipe. All right, so knowing all this cool and kind of scary physics, how do engineers actually put it into practice? How does this understanding help them manage our water systems better in the real world? Well, they start by separating the problem into two different types. First, there's what they call background seepage. You can think of this as death by 1,000 cuts, all the tiny little drips from joints and fittings all over the city.
And then you've got the big one, a pipe burst, a single, catastrophic failure at one specific spot.
Now, with advanced software, they can model all of this with incredible detail. It's like building a digital twin of the entire water network. First, they tell the computer what every single pipe is made of. Then, they set a tiny value for that citywide background seepage. And here's the magic part. They tell it how much that leak will expand depending on the pipe's flexibility. Then, on top of all that, they can simulate a huge pipe burst to see how the whole system holds up.
So, that's some pretty amazing science, right? But let's pull back and ask the big question. What's the real-world impact? Why does modeling a leak with this much detail actually matter to our cities and to us?
Well, the payoff is huge. By understanding this physics, water utilities can make much smarter decisions. They can pinpoint exactly which pipes are most at risk and need to be replaced first. They can actively manage the pressure in the system to keep those flexible pipes from stretching their leaks. All of this saves water, sure, but it also saves the immense amount of energy it takes to treat and pump that water in the first place. It's about conserving our most vital resource.
And that leaves us with a final thought. In a world where water is becoming more and more precious, getting this right isn't just a neat engineering exercise. It's absolutely essential for our future water security. We simply can't afford to guess what's happening in the thousands of miles of pipes right under our feet.